So for today's demo, we're going to be learning about the implementations of the algorithms that we talked about in the lecture. So first of all, we introduced the insertion sort algorithm, and then we talked about one algorithm for each of the three algorithm strategies. So let's implement all of those today and maybe a variation or two of them in order to learn about them a little bit more deeply. So first, let's learn about insertion sort. So I've taken the liberty of copying the pseudocode from the lecture into the code here into a comment. Obviously, we need to convert this into Python. So I'm going to convert it to snake case and use the appropriate standards, but also convert the for loops. One of the most important things that I'm going to do is to make sure that I use zero-based indexing instead of one-based indexing. So that's going to be one of the key differences here. Otherwise, honestly, there isn't that much different about these two, about pseudocode and Python. Now I am changing the name to insertion sort because that makes a little bit more sense. This insert-sort was something that I actually took from that famous algorithms book that I mentioned in the lecture. So that's an important detail that I'm changing. I also would really like to change the name of this variable because it appears so often in the code. I'll just keep it A. I'll just make it lowercase a so that at least it's appropriate. All right, so first of all, let's just convert this for loop. So the for loop in the pseudocode goes from index 2 all the way to and including the length. We want to go down by 1 because we want to use zero-based indexing, but otherwise the process is the same. We can still use the same variable for j in range, and I'm going to go from 1 to the length of a. And the reason I'm going to the length of a here is because remember that the range function doesn't include the end number here. So it's going to go from 1 to the length, not inclusive of the length. Okay, so that's roughly equivalent here. The next line is exactly the same, so we're just going to take a new key variable, and put the value at position j into that key variable. This is us removing it from the list temporarily so that we can shift some of the other values in the list with an empty space there. So now what we want to do is we want to go through all the indices before j, and there should only be one on the very first iteration because j starts at 1. There is an I equals 0 index that we want to consider. And any of those values that are larger than the value that's in key need to be shifted over by 1 at a time, until we encounter a value that's not larger. So we start at the position immediately to the left of j. So I'm going to set I equal to j minus 1. Okay, and that's equivalent to line 3. Line 4 is just going to be pretty much exactly the same thing. So in this case, I want to say as long as I is greater than or equal to 0, because originally we had if I is greater than 0, because 0 is not a valid index in pseudocode, but it is a valid index in Python. So I'm going to say greater than or equal to 0. And we're also going to check to see if the I value is greater than our key. So that's effectively the same. And remember that we have these two conditions, right? I is a valid index within the list, and also the value at position I is greater than the key. If that's the case, we want to shift the value at position I over by 1. So to do that, we're just going to say a at position I plus 1 is equal to a at position I. That's exactly the same as what we've got up here, except for the variable name being lowercase. And then I'm going to decrease the I value. I may as well use the Python shortcut, which is subtract equals 1. That's going to decrease I by 1, and this could go to the next value. As soon as I encounter a value that's not greater than the key, I stop the while loop, and I move on to the next j value. Okay, but before I do that, I need to insert the key value back into the empty space. So one of two things is going to happen with this while loop. One, I'm going to go all the way to the beginning of the list, having moved over every single value, because as it turns out, all of them are bigger than the key value. Key value happens to be the smallest value so far. That's fine, and that will exit when this condition is not true, because this is an and, either one of these two being true, either one of these two being false will exit the loop. And then the other situation that could cause this loop to exit is when I encounter a value that's not greater than the key. And that's fine, but either way, either in the first case, the first position of the array is going to be empty, and that's where I'll insert the key. And in the second case, wherever I found the very first not larger value than the key, I'm going to insert the key just to the right of that. Okay? So I'm just going to say a at position I plus 1 is equal to key. So I'm putting key back into the array at this point, back into the list at this point. All right, let's give this a quick test just to make sure that it works. So I'm going to say something like, let's say names. No, let's do marks, let's say. I'll just put a bunch of marks in there. We'll use some floating point values, let's say. So let's do 90, and then 35.5, and then 56, and then 75.25, and then 81, and then 47, and then 99, and then 83.5, and then 53.25. There we go, got a bunch of marks, and they're in kind of a randomized order. So let's actually call insertion sort. Now just keep in mind this is an in-place sort because we're actually changing A. I'm literally moving values around in A here. You can see that I'm taking a value out of A and putting it back here, and I'm literally shifting it over by one position here. So this is going to change the actual list. So this is a pass by reference. If you remember in Python, whenever you pass something like a dictionary or a list, it's passed by reference. So if I change A, it's going to change the original value. So in this case, if I say insertion sort marks, and then I do print, let's do that, and then I click run here, you can see that it sorts them, and the actual marks array now is in order. The old unsorted array is gone, replaced by this one. It's sorted in place. That's a good thing in the sense that it didn't require us to have any additional space. And it's also a bad thing because we maybe needed that unsorted version of the list. Who knows? Okay, let me just take a drink here. Okay. So what I want to do now is I want to figure out how much time this is taking. Like, I don't actually care about time because my computer might be faster or slower than somebody else's computer. What I really care about is how many operations I'm doing. So when you're doing this, the thing is to find out what kind of operation is representative of how much work this algorithm is doing. So like I could literally count all the operations. We kind of don't have the required understanding to do that because you'd have to take the computer architecture class and understand about assembly language in order to see underneath it all, what are all the, like, how does a for loop work? What's all the stuff that's required in order to get that for loop working in terms of basic instructions. Besides, it's not necessary anyway. That's way more work than I actually want to do. In my opinion, we're doing more work if we're moving more values around. So looking at this algorithm here, I can imagine that I don't really have to shift any values around at all. In that case, that list should sort pretty quickly. Like imagine I pass insertion sort, I pass an already sorted list to insertion sort. In that case, it shouldn't really do that much work because it doesn't have to do any of those shifting of values outright. We just take the value out and we put it back in the exact same spot where it started. If you remember the animation last time, that's how it worked. So I would expect it to do less work in that situation. So the number of times that we set a value or remove a value in the list is a good representation of how much work we're doing. So let's actually count the number of moves. So let's create a variable called numMoves. I'm going to set it to 0 at the beginning of the function. This is convenient because this function doesn't have a return value. So all I'm going to do is I'm going to make a return value be the number of moves. Okay, so right here you can see that we moved a value right here. And this is happening inside a while loop. So immediately after moving the value, I'm going to increment the number of moves. Okay. And then here I'm also moving. If you think about it, it's kind of like this line and this line together that are doing it. But I take the key out and then I put the key back in a different spot. That's a move as well. And I'm not really moving any values anywhere else in the code. So at the very end of the program, I'm just going to return numMoves. Okay? So just for the sake of it, let's get numMoves. And then what I'll do at the end of this list is I'll also print out no moves. Okay, let's see what that does. And this is going to be very informative, unfortunately, because this is a one single data point, and I don't know how this translates exactly. So we've got 9 values in our list, and that turned out to be 24 moves inside the list. All right, but let's take the already sorted list. So luckily I've got it printed out right here. I can just copy and paste it. So what I'm going to do is I'm going to comment this out, and I'm going to put the sorted list in there, and let's run it again. And we should see that we're moving fewer values. I'm not moving 0 values, I'm moving fewer values. The reason why we're moving 8, by the way, is because I'm going to take the 47 out. Like I'm skipping the 35.5 because we always assume that the first value is already sorted. We take the 47 out, but then we have nothing to move, so we just put the 47 back. So technically we're not really moving a value, but I did have to assign a value to a position in the list, so we'll count it. And then this one gets taken out and put back. Taken out, put back. So there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of those values. The 24 values, on the other hand, were because we took this value out, we had to shift the 90 over and put the 35 back. And then we took this value out, we shifted the 90 over and we put the 56 right here. And so there's more values. You can see in this case, this 47 would have to get shifted out, move over this value, this value, this value, except for the 35.5, we move the 47 into the second position. And so we have to move more values because this is a smaller number. And the 99 is a really big number, so we wouldn't have to move any of these numbers over. But then the 83.5 is smaller than that, so we would have to move the 99 over and the 90 also, because they're both bigger than the 83.5. So depends on the circumstances, right? If the list is sort of randomized, we're going to get some kind of an average. And so this 24 here is just like a typical value, but it's not very representative. So I think what I would like to do is let's do a worst case analysis. So the worst case for insertion sort, and for in fact a lot of sorts, is when the list is actually in reverse sorted order. Okay, so what I'm going to do is I'm just going to put in these values in reverse. So it's going to be 99 first, 90, 83.5, 81.0, 75.25, 56, 53.25. I didn't type any of these wrong. 47.0 and 35.5. Okay, so there is the exact same list, except this is in reverse. Let's run it again. And you can see that we add more moves, and that makes perfect sense, right? Because we move the 99 out of the way. The 90 needs to be over here, so we move the 99 over, and then we put the 90 in. And then when we take the 83.5 out, we have to move the 99 and the 90 over, and then we put the 83.5 here. So we're going to be moving like the maximum number of values in this situation. And so this is a really good representative of how much work we're doing. So I think what I'd like to do is I'd like to generate a list. So instead of this whole marks thing, let's actually just call it test list. And what I'm going to do is I'm going to set test list equal to range. So let's say, for example, I want to put in range. And let's say, for example, I want to put in 1,000 numbers. Well, this is going to take all the numbers from 0 to 1,000, but not including 1,000. And it's going to put them into a list. This list function here is just going to cause the range generator to generate all 1,000 values. But they're going to be from 0 to 999. They're not going to be in reverse order. So let's make them go in reverse order. So we want to start at 999, and we want to go all the way to and including 0. So we're going to go to -1 because we don't include -1. The one just before that is 0. That's where we want to stop. And we want to step down negatively. So this test list right here, let's just for the sake of it, let's print out test list. This is sorting it, so let's actually just comment that out. Shoot, I have the no moves here. Let's put those in 2 separate lines here. So let's put no moves here and test list here. So I can just comment out this one line. Okay. So running this program, you can see what the list looks like. It generates a big long list starting at let's make sure it's got all the right numbers, 999, and it goes all the way to and including 0. So that's a total of 1,000 numbers. And let's sort it. And we'll also print out how many moves we had to make in order to sort it. We can see that it is in fact sorted. So 0 is at the beginning now, and 999 is at the end. They look like they're in order to me, and it had to do 500,000 moves in order to accomplish that. Okay, so we're getting there. We're getting at some test code here. What I think I want to do is I want to test a whole bunch of numbers. So I'm going to put this in a for loop instead. So instead of marks here, I'm going to have a for loop. And let's call this list size in range. And what I'm going to do is I am going to start at 1,000. So I want to first test 1,000 elements. And I want to go all the way up to, let's say, 10,000. Okay, so I'm going to go to 10,001 because we're not going to include that. And I want to jump up by 1,000 every time. It doesn't really make sense for me to test 1,000 and then 1,001 and then 1,002. If I can just test 1,000, 2,000, 3,000, 4,000, 5,000, that would be much better. So let's put this code inside the list. And instead of going to 999, what I'm going to do is I'm going to go to list size -1. Okay. I am not going to want to print out test list anymore because that's going to generate a huge amount of output. We're going to have, 1,000 elements and then 2,000 elements and so on. It's going to be very big. So instead what I'm going to do is I'm going to say list size. I'm going to just print out the list size. And I know it's just going to be a list from list size all the way down to 0, right? So I don't need to see the list. So I'm just going to print the list size and the num moves. In fact, let's put it on the same line again. And then we'll get our data. Okay. So here we are anyway. This is, by the way, going to take a really long time, and you can see the numbers. This is the reason for it taking so long. We're talking about 18 million shifts here, okay, and 24 million shifts. And it's going to increase over time, as remember that this is an n-squared relationship, and n being list size in this case. So we're talking about 10,000 squared. Anyway, so you can anyway see that this is growing really quickly. So we ended up having, what was it, what's that, 50 million? Yeah, 50 million shifts. I'm not sure why that ran again, but anyway, we've got our values anyway. So we could plot these values if we wanted to, and then we could see what the performance of this is. And this is effectively what I did for the chart within the slides. Alrighty, anyway. So we'll let that go in the background. It's almost done. Let's now move on to binary search. So binary search was an example of a divide and conquer algorithm. I've got the pseudocode here, so let's write a Python version. I'm going to call it binary search with snake case. We're going to have X for the thing that we're going to search for. Ugh, I don't like these variable names, but anyway, remember that variable names are really important. So I would usually, instead of X, I would usually write to find or search for or something like that, and then A would be the list or elements or something like that, a little bit more sensible. In this case, like, I'm not even sure which one's the list and which one's the thing I'm looking for because they're really terrible variable names. Anyway, it's fine, I guess. So now we've got binary search. So let's take a quick look at what we've got going on here. Okay. So in order to get binary search working, we're going to need to just convert this pseudocode into Python, which the key is really just making sure that we get the indexing right, but it's not really that different. So let's just go through line by line here. So line 1 is just checking to see if the start index and the end index are actually out of order. And that means that we have narrowed the start and end so much that there's nothing left. There are no elements to find. So that code just stays the same. I just say if the start is greater than the end, normally the start is less than or equal to the end. It's equal to the end if we're just pointing to one element, and it's either that element or it's not. And it usually start is less than, strictly less than end, And so if that's the case, where start is greater than n, there are no elements to search, so we can't possibly find it. So I'm just going to return false in that case. All right, then we're going to calculate the middle index. Middle index is going to literally be start plus end divided by 2. I'm going to use integer division to make sure that I end up with an integer. And then I'm going to do the 3 cases. If the x value is equal to a at position middle, that means we found it, so I can return true. So I can quit, basically. No need for any further recursion. Otherwise, if x is less than a at middle, then if you remember how binary search works, I want to search the left half. It was roughly half. Like we divide the list up in half, and I want to search the left half, although I also don't need to search the middle element specifically. So if the value is less than the middle, I only need to search the left half. I can completely ignore all the right half, which means that I can just recursively call binary search with the same x and the same a, but I'm going to change the start and end index so that I'm only searching the beginning, right? Like if the value is less, because I'm assuming that the list is sorted, if the value is less than a, if it does exist anywhere in a, if it's less than the middle element of a, then it must be on the left-hand side. So we don't need to search the middle position, and we don't need to search anywhere from the middle to the end. Okay, so instead what I'm going to do is I'm going to search from start to middle minus 1. And it's mostly the same here, you can see. And then the other case is, what if x is greater than? I'm actually going to write that out instead of the else condition, but obviously the else condition is a little bit more sensible. But if the x value is greater than the middle element, then I still want to do a recursive search. But remember that this is divide and conquer. I'm actually only conquering the portion of the list, because effectively I've eliminated parts of the list that definitely aren't places where we'll find that value. But in this case, if the value x is greater than the middle element, it can't be in any of the left part of the list because the list is sorted. So it has to be in the right part of the list. So instead of searching from the start of the list, I'm going to search from the middle of the list. Although I don't have to search the middle elements, I'm going to search from middle plus 1 all the way to the end of the list. There we go. So there is a binary search algorithm. Let's write some simple test code for right now, and then we'll move on to some more advanced test code. So let's, for example, let's put some numbers in there, and let's just call it numbers. Not feeling very creative right now. And let's put these in sorted order. So let's just put numbers that are a multiple of 10 just to make it easier. That way, if we search for something that is a multiple of 10, it's probably going to be in there. So let's just do that. And let's call it the number that we're looking for to find. So first let's look for 20. So 20 is in the list for sure, so we should find it. And all I'm going to do is I am going to have a print here. I'm going to say looking for to find in numbers, and then we'll put the result. So we'll say binary search, and we're searching for to find in the list numbers. And it's kind of awkward that I have to put 0 and the length of the list minus 1. So I could use some default parameters up here, but whatever. That's not what this is about, I guess. So I'm going to just use the length of numbers minus 1. All right, so there we go. That's our binary search result. So let's see if just make sure that it finds indeed that there is. Oh shoot! I gotta turn off all that sorting. Let's kill that. Okay, so let's actually comment this code out here. You know what? Let's just go from 1000 to 1001. That'll just do one iteration. That's pretty quick. Okay, so in this case, it's looking for 20 in the list, and it found it. So that's good. Let's look for 10. Beginning of the list. It should still find it, but it's at the beginning of the list, so it makes sense. That's a good place to test. Again, we're thinking like a QA engineer here. Now let's look for 100. That's at the end of the list. That should be there. It found the 100, so that's good. Let's look for one that's smack dab in the middle. Let's look for 50. You should find this one really quickly because it's probably the very first element that it looks at. All right, now let's look for values that it shouldn't find. So looking for 5, for instance, it's not in there. So we're going to look in the middle of the list, and we're going to work our way toward the front. We look at some animations kind of like this. It did not find it. That's good. Let's look for 105, which is on the right-hand side. Not found, but we should at least find it. Okay, looks good. Looks good. So what I think we should do next, yeah. By the way, you could do the same thing for insertion sort. You could count the number of operations. The only issue with that is you need a very, very big list to get any readings that make any sense. So you have to search like billions of elements for it because binary search is so efficient. Even in fact, if you have a list that's 4 billion elements long, that's only going to take you 32 numbers. You're only going to have to look at 32 numbers, which is quite negligible from a programming standpoint. So this is a very efficient algorithm. And by the way, you could turn this algorithm into a non-recursive version if you like. And that's an exercise I'll leave for you. But you could change it to a while loop. All you need to do in these if statements here is then change the start or the end variable. So in this case, I would change the end variable to middle -1. And in this case, I would change the start variable to middle +1. And then we'd go back through the loop again. And I have to obviously quit if I find it, or if I run out of, this will have to be inside the loop. But otherwise, the code is very similar to what you see here. Anyway, so you could write some code to count the number of operations if you want, but just make sure that you choose some really, really, really big values. Okay, so let's move on to the knapsack problems. It's a little bit more challenging to implement. Just because of the nature of the problem. If you remember, the knapsack problem is a problem where you have a bunch of items, and also you have each item has some value and it has some weight and so on. So I think what I'd like to do is I'll copy in some test code just to save ourselves some typing here. And I don't know what I was thinking. I'm not using snake case here. That should definitely not be the case. We should be using snake case. And this is obviously pre-f string. So let's convert it so that it uses an f string here. So we'll put an f at the beginning. And we'll call fractional knapsack in here. Curly bracket quote. Curly bracket quote. Okay, and I think I screwed that up somehow. So we got, you can see the colors match up. So we've got the blue. It's because we got single quotes in here. So let's use a double quote string here, just to make it easier, because these single quotes here are causing issues. Let's change it, or try to change it. All right, so this is basically what's happening here. Is this is calling the fractional knapsack function, which I haven't implemented yet, which is why it's highlighted. And it's passing to it a list of tuples. So you can see it's got these 3 tuples. And I've simplified it just because I want this to all appear on one line. So one option is we have some diamonds, and we have some gold, and we have some silver, and they have a value and a weight. And this is our knapsack capacity. So we're going to call it with a couple different capacities. Okay. So the next thing I'm going to do is write the function. So fractional knapsack, and that's going to take a list of items and the capacity of our knapsack. I have to give it the proper name because that is the name of the famous problem. Is knapsack, not backpack. Okay. So first, a couple of special cases. First of all, no items to take. So if we run out of items, then all I'm going to do is just return an empty string. So for example, if the number of items is less than 1, I'm going to return an empty string, an empty list. An empty list is going to indicate that I'm going to put nothing in my backpack. Another possibility is that we have no room for any more. So I'm going to say if the capacity is equal to 0, then I'm going to also return an empty string. And this seems weird, like what are the odds that I'm going to pass an empty list of items, or I'm going to use capacity equals 0. This is going to be a recursive function, and the recursive function is going to remove an item. Whenever I put an item in the backpack, I'm going to decrease the capacity and remove it from the list of items before I make the recursive call. So the number of items is going to decrease, and the capacity is going to decrease. So what I can do is I can check to see if the capacity is 0, check to see if the items is empty. And in fact, one thing I might do is I might check to see if the capacity is less than or equal to 0. Because just in case if I screw up my program, I still at least want the capacity to cause me to exit. I'll obviously have negative capacity, which means I put too much in my backpack, but no harm done in this case. It'll at least exit, and I won't be stuck in some infinite loop. Okay, so the first thing I'm going to do is I am going to choose the next best item. Okay, and I'm just going to choose that one at a time rather than sort them. I'm going to choose the best, i.e. highest value to weight item. So all I'm going to do is I'm going to say best index is equal to 0. Let's assume the first element is the best one, and then let's actually check. So for I in range len items, let's go through all the items. I'm going to just check if the current item, if item is at position I, and remember that these are a tuple, right? Each item is a tuple. Well, the 3 tuples represent the in this case, just for simplicity, I made them the values here. The second value is the value to weight. Okay, so this is the highest value. Okay, so instead of this being the value, this is the this is the value to weight. Okay. So I'm just going to say if the current item and at index 1, in other words, the value, is greater than the items at the best index, index 1, which is again the value to weight ratio. Of course, calculating the value to weight ratio is pretty trivial, but in this case, I've made my job a little easier by just setting this to the value weight ratio instead of having those two values be separate. If that's the case, then that's the new best index. I'm just going to set best index to I. So this is going to go through and find out which I has the absolute best value to weight ratio. If I was just doing it, then I could, if I was doing it by hand and not actually updating the value to weight ratio, then what I would do is I would say items at I1, let's say 1 is the value and this is the weight, because I think this is the value to weight ratio and this is the weight, if I remember correctly. And so this one, I would just divide index 1 by index 2 of this, and then I would compare that to the same calculation for best index. So anyway, it's not that much of a difference here. So now what I want to do is I'm going to determine how much of that item. This is a fractional knapsack, so no matter what, if I've got non-zero capacity, I can take some of it. Okay, so if, for example, there are two situations. If my capacity is greater than or equal to the items at best index at position 2, that's the weight, then we can take the whole thing. Okay, so what I'm going to do is I am going to grab the item, and this is going to be the name, and then also we'll store in the weight as well. So the weight is at index 2. So we'll just make a tuple out of this, which has the name and the weight of the item. And then I'm going to decrease the capacity by the items at best index 2. That's going to take off the capacity for the entire item. And then what I'm going to do is I'm going to remove this from my list of items. So I'm going to set items equal to items. And what I'm going to do is I'm going to take all of the items up to best index, not including best index. If you remember, that's how the slice operator does. And then I'm going to concatenate that list with all the items after best index. So that's going to be best index plus 1 colon. And if you leave out the second part of the slice operator, it goes all the way to the end. So it's going to just basically take all the values except the one at best index. And then I put that back into items, the same exact variable. So then all I do is I'm going to recursively call, because I probably still have some capacity left. So I'm going to say return fractional knapsack, recursive call with my new items list and my new capacity that I've just updated. But this is going to return all the values from this smaller list of items that I want to carry with the smaller capacity left. It's going to return a list of all the things. So I'm actually going to concatenate to that carry. And the reason why carry is in square brackets here is because carry is a tuple, and I don't want to like glue tuples together. I want a list of tuples. Each tuple contains the name of the item and the weight of the item that I want to carry. And in fact, why the weight? Honestly, I should be actually grabbing all three things. We should just grab the entire, item. That way it's got the name, the value to weight ratio, and the weight. That actually makes sense to me. Okay, now the other situation is we need to take a fraction of it. And then that'll basically finish the job. So what we need to do is figure out how much capacity we have left. So what I'm going to do is I'm going to figure out the capacity of it. So we're taking all of the items here. And so all I'm going to do then is, maybe just for simplicity, I'm just going to set carry equal to items at best index 0, and then items at best index 1, so that'll give me the value to weight ratio, and then items at best index, and then capacity. So this is how much of that item I'm going to take. Instead of the whole weight, I'm only taking the capacity. So then what I'm going to do is I'm going to return this carry value at the end. Okay? And so the way that it's going to work is I'm going to grab, so for example here, with the capacity is 20, I'm going to grab the most valuable value to weight item, which is the diamonds here. And that's going to occupy 8 of my 20. And then it's going to recursively call fractional knapsack with a list of items that doesn't include diamonds, so just gold and silver. And the capacity is now going to be reduced as well. So our capacity is only going to be 12 in that case. And then that recursive call to fractional knapsack is going to choose between gold and silver based on a capacity of 12. Well, we can't fit gold in there, and so we have to move on to the next possible item. Okay, all right. Let's just check to make sure this seems to be working. And we're running it with 2 different capacities, so let's take a quick peek. So in the case of the first call, where we have 20, we end up taking the gold and the diamonds. The way that I've concatenated these together actually means that I put the item that I grabbed first on the right-hand side, but that doesn't really matter. What's in the backpack gets tumbled around or whatever anyway. But you can see the weight here is that we have, we took 8 of the diamonds, which is all of the diamonds. And then we took gold because the gold had the next value, highest value, but we couldn't take all of the gold. So we took 12 of the gold. All right. And then in the case where we had 25, we took the diamonds and we were able to take all 8 of the diamonds. And then we took the gold and we were able to take all 13 of the gold. And that was a total of 21. So then what was left was we took 4 of the silver. Okay, and we can calculate from that the value to weight ratio by multiplying these 2 values together. And we should be able to see in this case that we have the maximum amount of money available. All right, so finally, one more thing to do is to implement the efficient Fibonacci example. So we've already seen the bad Fibonacci, really simple Fibonacci. For simplicity, for reference here, I'll post it. Here's the example of the Fibonacci code that we might use, but this is very inefficient. And let's just prove that real quick. Let's just try to calculate the 30th Fibonacci number. And anyway, okay, actually that's not so bad. Let's do something like the 50th Fibonacci number. This could end up taking a really long time. And we talked about how this is a real huge duplication of effort. Okay, so the 50th Fibonacci number takes a really long time. Let's let that go in the background, just in case it finishes, while we write the better Fibonacci. So let's call this Fibonacci. I'll call it _DP for dynamic programming. Okay? What I'm going to do is I am going to include the solutions. So basically what we're going to do, I'm going to try to keep it as similar as possible to the Fibonacci implementation that we've got. But I am going to build up a list of solutions, and I'm going to go from smallest to biggest. So first of all, let's create two base case solutions, and those are just 0 and 1. Those are the first two Fibonacci numbers. That's the starting point for the math definition, so that makes sense. And then we have a base case where I'm going to say, well, if the number that I'm looking for is less than 2, then let's just return solutions at n. Now, I don't, since it could be negative, I probably should handle that case, but for simplicity, I'm going to trust my users this time. For any value that's greater than 2 or greater than or equal to 2, we're going to have to calculate it. So what I'm going to do is I'm going to go over all the numbers between 2 and n plus 1. That way I actually include n, but not include n plus 1. And basically what I'm going to do is I'm going to calculate the next Fibonacci number. So maybe let's say something like ith Fibonacci number is equal to solutions at I minus 1. I'm going to look it up in the table. And the first index is 2, so I minus 1 is going to be 1, which is already in there. You can see it's here. And then I'm going to add to that the solution for I minus 2. And that's basically the definition of Fibonacci. So I have a typo here. And again, for the first index, that's 2. 2 minus 2 is 0. That one's in there as well. And now I'm going to add this to my list. So I'm going to say solutions dot append. I'm going to put the ith Fibonacci number in there. And then on the next iteration, it's going to be I equals 3, which is going to use 3 minus 2. 3 minus 1 rather, which is 2. And that's going to be the 1 that we just added. And then it's going to be 3 minus 2, which is 1, which is definitely already in the list. So as we build from the bottom, from the smaller indexes upward, we're always going to have the previous two Fibonacci numbers in our solutions list. Okay? So what we're going to do is just return solutions at index n, which is the last one that we would have calculated. Okay, so you can see that the old school Fibonacci hasn't finished calculating Fibonacci of 50. I don't know if it would finish today if I left it going all night. So I think what I'll do is I'll comment this out, and I am going to do the same thing but with our new function. So we're going to call Fibonacci dp with 50, let's say. And we should see a response much quicker. Okay, so you can see, anyway, it worked much more quickly. Let's try 500 just for the fun of it. Obviously, this is going to get to be a pretty big number, but it's still very, very efficient. So it's able to calculate the 500th Fibonacci number because we're not doing any of the duplicate solutions anymore. So it sounds like a really minor improvement, but this is actually enormous. We have reduced the performance, we have increased the performance of this, reduced the amount of work that needs to be done by like 99.99999% here for this particular case. All right, anyway, so those are 3 algorithms using the 3 strategies that we learned about. You can apply these same strategies to numerous other problems. And you're going to see these strategies again and again. You're going to see dynamic programming solutions, divide and conquer solutions, and especially greedy all the time. A lot of the most famous algorithms that you're going to learn about over the next couple of years are going to be one of those 3 strategies. Not all of them, but most of them. Anyway, so thanks a lot, and I'll see you next time.